Albert Einstein based on the quantum calculations of the mathematician physicist Sachendranath Bose and the apparition of the Bose theory that particles like electrons could be described as waves, predicted the existence of a new state of matter, the fifth state of matter. Well, what's a Bose-Einstein condensate then? A Bose-Einstein condensate is the fifth state of matter after the solid, the liquid, the gas, and the plasma. It's a state of matter where gas particles are cooled down to a temperature close to absolute zero. As we are getting close to absolute zero, the particles turn into wave and share the same energy level. All the particles have turned into wave and can be described by a single wave function. It will then naturally occur in space, which is wow. Now let me list you all the equipment and ingredients needed for its creation. For the ingredient, we only need one category of particles called bosons. Bosons are the messenger forces of the universe, such as the electromagnetic force, the strong nuclear force, and the weak nuclear force. But that's their usage really. A boson in itself is a particle with a whole integer quantum mechanical value, often referred to as a Bose-Einstein statistic. In fact, any atom with an even number of proton, electron, and neutron can be thought of as a boson. For the equipment, we only need lasers and magnets. That's it. That's just all we need to make a Bose-Einstein condensate. Not at home. No, it's trickier than what you think. In fact, in 1995, Rick Cornell and Carl Wieman created the first Bose-Einstein condensate using rubidium-87 atom. They've cooled down 2,000 particles of rubidium-87 atom to a temperature of 200 nanokelvin. That was the lowest temperature reached at their time. They showed the motion of the particles on a two-dimensional velocity distribution. A few months later, Wolfgang Ketterle did the same using sodium atoms. They all shared a Nobel Prize in 2001. Well, since 1924, with the discovery of matter on linear momentum exhibiting wave-like behavior depending on the magnitude of the momentum, scientists are able to explain the transition of matter to wave. This is the so-called de Broglie wavelength after Louis de Broglie. The momentum is also related to the temperature. Greater temperature implies greater particle motion means hot. Less temperature implies less particle motion means cold. Therefore, from the equation, we can conclude that the less particle motion, the longer the wavelength. This is what's happening with the Bose-Einstein condensate. The ability of bosons to be so social allows them to share the same energy level. Thus, when the particles turn into wave, they share the same energy level, and these waves overlap to form one single entity. This is where a Bose-Einstein condensate is given birth. Now, once we have reached the Bose-Einstein condensate, the behavior of the particles are dictated by a mathematical tool used in quantum mechanics, the so-called scattering length. The scattering length is the description of the interaction between particles. In general, the scattering length can be calculated using various mathematical models and techniques, dependent on the conditions. In the case of a Bose-Einstein condensate, we are expecting for a negative scattering length, in which the particles interact longer and longer, kind of like an inelastic collision. To determine the scattering length, we can derive the Gross-Pitevsky equation. By using this concept, physicists are able to calculate the probability of particles scattering off each other. The Bose-Einstein condensate is classified as a quantum degenerate. A quantum degenerate is any collection of particles exhibiting quantum behavior at extremely low temperature. To create a Bose-Einstein condensate, we only use two methods of cooling, the laser cooling and the evaporative cooling. The laser cooling is the process of shooting lasers into atoms in opposite direction. Particles absorb the energy of the light with a frequency slightly higher than the transition wave. The particle doesn't know how to handle all this energy, and finally emits back all this energy, but in all directions. Thus, no net force is observed, and the particle slows down, therefore cools. 6 lasers are placed in different directions for better cooling. Unfortunately, lasers are not infinite. They have to be recharged with photons. By that time, the particles regain energy, therefore becomes hot again. So we introduced the new concept of the evaporative cooling. This is when we take all the bombarded particles and trap them into a strong magnetic field. The hot particles are evaporated and the cold ones left behind. And this is when we got a Bose-Einstein condensate. Bose-Einstein condensate brings with it some interesting quantum phenomena at macroscopic level, such as the superfluidity, the flow of fluid with zero viscosity, and the superconductivity, which allows current to flow with zero resistance. It does also have some interesting properties. It is chemically inert. It means it doesn't react with any other compound. It has to be kept in the dark because any source of light can warm it up, even an incandescent light bulb. And it is able to slow down light to a few miles. Here are some few applications of the Bose-Einstein condensate, not many of them, but real interesting ones, such as the gravitational sensor. I'm really impatient to see how it will work. Alright, this is it. I hope you have a better understanding of the Bose-Einstein condensate, the scattering length, and the cooling methods.